We've already learned how to calculate the electric potential when we know the electric field, and more specifically, how to find the electric potential at a point when we have point charges creating our electric field. This video will focus on finding the electric potential at a point when we have a continuous charge distribution. Specifically, we'll look at an example of when we have a line of charge creating our electric field. In general, if we have a 2 or 3-dimensional charged object, we need to begin with an expression for the electric potential caused by a small amount of charge. Now, this should look pretty familiar to you since this follows along the same method that we've used multiple times. So let's say that we have a small piece of charge that acts like a point charge. We know the electric potential from a point charge is kq over r. And so if we have a little bit of charge, we have a little bit of electric potential, k dq over r. And then, of course, we're going to add up the electric potential from each of these values of charge, from each of these little bits of dq. And as we've seen in the past, that means that we're going to use an integral. Just like when we derived an expression for the electric field before we learned Gauss's law, we're going to need to use the linear charge distribution, surface charge distribution, or the volume charge distribution to substitute something else in for dq most often. So let's look at an example of doing this when we have a line of charge. So here I have a line of charge of length L, and I'm trying to find the electric potential at a point P that's above one end of that line of charge. The other thing that this problem tells us is that that charge is uniformly distributed. And that'll be important for us to think about as we're deriving our expression. So again, we start with a little piece of charge. I'll mark that little piece of charge here. That's dq. And actually, we'll see that in the next diagram here. A little bit of charge dq has a length of dx. It's located a distance x from our left end, and it has a distance r from the point where we're trying to find the field. So the little bit of potential from that little bit of charge, dV, is equal to k dq over r. Now, because we have a line of charge, we're going to focus on a linear charge distribution, which says that lambda is equal to the total charge divided by the total length. And that also means that our little bit of charge dq is equal to lambda times the little bit of length of our charge dx. So we know we're going to take the integral of both sides of this expression, and plugging in for dq, I have k lambda dx divided by r. Now I know that r is going to vary as I choose different pieces of charge, and the variable that I have here is x. And so that means I want to get r in terms of x. Taking a look at my diagram here, I see that I can express r in terms of d and x, because r would be equal to the square root of d squared plus x squared, making use of the Pythagorean theorem. So I'll plug that into my expression here. K lambda dx divided by the square root of d squared plus x squared. Just as we've typically done in the past, I'm going to pull out constants. And we know that k and lambda are both constants. And I'm also going to put limits on my integral. X is my variable. And I can see that the smallest x could be, or remember, x is the distance from the left end. So the smallest it could be is 0, and the largest it could be is capital L. Now, taking a look at this integral here, this would fall under the category of integrals that we cannot easily solve, which means that we're going to look up that integral in the table in the back of your textbook. If I find that integral in that table, it's written as such in your textbook. It says that the integral of dx divided by the square root of d squared plus x squared. Actually, your textbook uses an a, so we'll just be consistent with what it says there. A squared plus x squared is equal to the natural log of the quantity x plus the square root of a squared plus x squared. So the only thing that's different between our expression and what was in the back of your textbook is our a is instead a d. And so we can say that our integral is evaluated to be the natural log of x plus the square root of d squared plus x squared. And then, of course, we have to plug in our limits from 0 to L. So plugging in those limits, when I plug in L, I get L plus the square root of d squared plus L squared. And then when I plug in 0, I get just ln of d. Now, we know that natural log is a function that we can kind of change when we have a subtraction of two natural logs. So instead of writing this as this big expression that's in parentheses here, I could write this as the natural log of the quantity L plus the square root of d squared plus L squared, all divided by d. There's no further way to simplify this expression. So this is my final expression for the electric potential at our point P, which is above one end of our charge. Now, actually, I misspoke a little bit. I realized that what's given to me at the beginning is not the charge density, but it tells me that its length is L and its charge is Q. So instead of having lambda in my final expression, I'll just plug in the Q over L as my final expression. So K Q divided by L times the natural log of what I have in parentheses there. Again, just as we've done in the past, you are required to know how to do this derivation. And so I suggest any time that you are doing a problem where there is a potential needed above a line of charge, that you do the derivation to make sure you become comfortable with the various steps.